Okay, can I start?
Yeah.
All right, so I was asked to talk about the orderon at the EIC. This is a great author paper on just that. And actually, the main message of this talk, you can already see in the title of this talk, I say the orderons, it's a plural. And by this, I mean there are different types of orderons which we know how to classify systematically. So here's the contents of my talk. So first, I will talk about orderon in DIS, which is which is experimental electron ion collider. Then I show that we can classify orderons using the so-called generalized TMD or GTMD, which is a Fourier transform of the Wigner distribution functions, and use this knowledge to calculate the cross-section observable at the EIC. Then I will make a loose connection to the orderons that was discovered at LHC. Well, the connection is not very strict, but I will indicate how you might be able to connect the orderons in these two experiments. And at the last, I will talk about the orderon in Adhdft. And I didn't originally plan to talk about this, but when I looked at the list of participants, I saw many people who might be potentially interested in this subject. And in particular, we have Chun-Yi in the audience. So maybe this is a good opportunity because I never presented about this work to these people. So we have already heard about lots of exciting things about the orderons, which made headlines recently about the discovery of orderon, LHC, in this deep region about d sigma dt and the proton-proton collision at LHC. And this was already covered by Tim this morning. But on the other hand, what about EIC? So there are three pillars, scientific pillars of electron ion collider, and this is small x, and the spin physics and tomography. And where does orderon sit in this diagram? And if you look at the white paper in 2012, then there is absolutely no mention of orderon in this white paper, in 200 pages white paper. And so, but I think this has to change because in my opinion, orderon is actually a quintessence of the EIC science. It is of course connected to small x physics, but it also has connection to the spin physics and also the tomography. And so the orderon is really at the center of the EIC physics. So I want to explore that in that direction. So how do I see orderon in DIS? So this, as already mentioned by Leszek, the classic discovery channel of orderon is in DIS is exclusive pi0 and eta c production. And the reason is simple because the photon is coming in and pion is coming. So photon is She-odd and orderon is She-odd. So the end result product is She-even mesons such as pi0 and eta c. And so this is a classic signal of orderon in DIC. And also this has been, it has been proposed, suggested by this gentleman that one can also look at the two pion production in the same experiment. So instead of having a single pion, you can have two pions, pi plus and pi minus. And for theorists, in order to apply the perturbative approach to this process, we need a large Q square, or you need a large heavy meson like the She. To have some hard scales, but the experimentalists don't care such things. And if you find this process at Q square equals to 0, that's still a signal of orderon. And indeed, this has been measured previously by the H1 collaboration at Terra. And the result was actually a disaster. So this is a paper which was published in 2002, and they measure this process, and the conclusion is that it's basically no result, so no signal of pi0. So they made an experimental upper bound of the cross section, and so this was, well, I think this was a very huge disappointment, and I feel that the community was traumatized by this no result. But I want to point out that there is something very unusual about this measurement, and that is so instead of measuring the proton in the final state, they look for the neutron in the final states. So they consider the process where the proton is first excited to the N star. It's a negative parity baryon resonance, and this N star decays into neutron and pion, and then they look for this neutrons. So why did they do that? Instead of just measuring the elastically scattered proton, they measure the neutron. And that's actually a very interesting point, which I plan to come back to this point later in my talk. All right, so this is already covered by Leszek, but let me just repeat. So here, mostly talk about the BFK aspects of Orderon, but I'm more familiar with the color glass condensing type approach. So small x limit of QCD is basically an effective theory of Wilson lines, and the basic object in DIS is a so-called dipole S matrix, which is a product of Wilson line and the complex conjugate of the Wilson line, which represents the iconal propagation of a quark and anti-quark, and U is a Wilson line. Now, the Orderon, you can identify Orderon as the imaginary part of the S matrix, which means the real part of the amplitude. So this S matrix in general has a real part and imaginary part, and Orderon is imaginary part. And why is that? Why is this Orderon? Because it flips signs if you interchange X and Y. And if you flip X and Y, that means you interchange between quark and anti-quark. So that means that this imaginary part is She odd. And that is a decisive property of the Orderon. And we know that how this amplitude evolves with energy, first derived by Urey in the large NC limit. And we also derived in a complete independent method and finite generalizing this equation to the finite NC. So this is an equation already mentioned by Leszek, and there is a nonlinear coupling between Orderon and the Pomeron, which suppresses the Orderon if there is a saturation effect. Okay, so now I come to the very interesting recent developments. We have Orderon families. Orderon is not unique. There are several different types of Orderons, and you can see that from this basic consideration. So we have this amplitude O, which is a function of X and Y, the position of quark and anti-quark, and this is odd in R. It's a relative distance, X minus Y. So this amplitude must be proportional to this vector R, but O is a scalar. So there must be another two-dimensional vector to contract indices to make it a scalar. And there are two possibilities. One is the impact parameter, B, which is the sum of X and Y. And that means, so the Orderon amplitude is a dot product of R and B. And since there is a B, this has a connection to the tomography of the proton. And the second possibility is if the proton is transversely polarized, then there is a transverse spin vector S perp, and we can have Orderon amplitude proportional to the R cross S. And that makes a connection to the spin physics. So what I want to say here is that in order to completely define the Orderon, you need a transverse momentum, which is conjugate to R, and also the impact parameter B and the spin. So we need both R and B, and that means, and that brings me to the Wigner distribution function. So here's the Wigner, this is a quark Wigner distribution function. It's a phase space distribution function, both having a transverse momentum and a transverse position. And this is often quoted as the mother distribution function, because if you successfully integrate K and B, then you can reproduce all the lower dimensional pattern distribution functions. And the best way to characterize Orderon is to use this Wigner distribution function, or its Fourier transform generalized TMD. So GTMD is a function of X and K perp and delta perp, and delta perp is Fourier conjugate to the B perp. And in this paper by Renaud and other people, this is a most general parameterization of Orderon matrix element in proton states, the non-forward matrix element. And there are three independent GTMDs, G11, G12, and G13. So there are three Orderons, and these are completely independent, and you can access them in different kind of experiments. All right, so one thing I'm mostly interested in this G12, which is in here. And this is, we have sigma tensor here. So this has to do with the spin of the proton. And if, in particular, if the proton spin is transversely polarized, then this spinor product reduces to this cross product of K and S. And if you are familiar with the spin physics, then you immediately recognize that this is the same structure that you find in the definition of the Chivas function. So this is a TMD of quark and gluons. And if the spin is transversely polarized, and there is an extra term which precisely has this structure, K cross S, and this coefficient is called the Chivas function. So that means that this G12, the orderon, one of the orderons, is proportional to the gluon Chivas function at small x. This is a very important observation by Jiang Zhou in 2013. And I guess many people in the audience don't know about the Chivas function, so let me just spend one slide about this. So there is a phenomenon called the single spin asymmetry. We have a transversely polarized proton colliding with the unpolarized target, and there is a left-right asymmetry in the produced hadron species. And so that means the cross-section has a path which is proportional to K perp, where K is the transverse momentum of the final state hadron, and S is the transverse spin of the incoming proton. So there is a sine phi asymmetry in the final state distribution function, and this is caused by the Chivas function. There are many other mechanisms, but one of the promising origin of this phenomenon is the Chivas function. And this has a very long history, and lots of measurement has been done. But so far, most of the studies have been focused on the quark Chivas function. But recently, there's much interest in the possibility to access the gluon Chivas function especially at the electron-ion collider, for instance, in this reference here. So that means that there is a novel connection between orderon and the single spin asymmetry. So this is a really unexpected connection between the two. So you can actually calculate this Chivas function. Well, we can calculate the energy dependence of this Chivas function because we know the evolution equation satisfies these amplitudes. So we can solve this nonlinear orderon equation starting from the initial condition like this. This sine phi, this is a characteristic of the Chivas function. And you find this plot that Leszek already showed. And so this is a R, the transverse momentum. And you see the peak position does not change. So this means that there is no geometric scaling for this orderon part. This is a profile of the proton. So the proton spin is polarized in this X direction, and there is a left-right one, which is up and down symmetry in this plot. And that is caused by the gluon-Chivas function for the orderon. All right, so you might think that so G12 mass is uniquely to do with the process involving the transversely polarized proton, but that is not necessarily the case. In fact, the same spinor product, which involves this sigma mu, is also non-vanishing if the proton spin flips. So if the transversely polarized case, you have this cross product. But if the longitudinally polarized case, and if this proton LHC flips, then this is again non-zero. So this means that we can actually measure this quantity if you look at the process where the proton spin flips. And that does not necessarily require the polarized beam. And I want to emphasize that contrary to the prevailing belief, the spin flip amplitude may survive at high energy because the orderon intercept is 1, if you don't consider the saturation. But the fact that we observed the orderon at the LHC suggests that there are some orderons surviving this LHC energy region. So usually this kind of spin flip amplitude is assumed to be tiny at small x and usually neglected, but it may not be the case because this has the connection with the orderon. All right, so this is the main prediction of our paper last year. So we considered a EIC unpolarized scattering of lepton and proton, and we look at exclusive final state with 1 pion and proton and nothing else. And this, if you look at the t equals to 0 in the very forward limit, then one can show that this cross-section is dominated by the spin flip contribution. So the proton spin flips, and this is the only surviving contribution. The spin non-flip part is suppressed when t goes to 0. And here's a formula for the cross-section, and it explicitly involves the Shiba's function. So this is a very unusual situation, because usually the Shiba's function is associated with the transverse inverse spin asymmetry, but here this is unpolarized cross-section and still dominated by the Shiba's function because it's connection to the orderon. So this is what I would expect. This is just a cartoon. Don't take it too seriously. But this is my suggestion to where to look at the EIC, the pion production as function of T. And we have a contribution from the spin-dependent orderon, which is non-vanishing as T goes to 0. And there is another contribution from the spin-independent orderon, but this goes to 0 as T goes to 0. And there is a background called the Primakov effect, where you have an exchange of a photon in the T channel, and this blows up as T goes to 0. So there's a competition between these two effects. And if you're lucky, then we might see this proto, and that is a signal of the orderon here. And I want to emphasize that this non-vanishing behavior as T goes to 0 is very non-trivial. And this connects to the experiment which was conducted by the H1 measure. So as I said before, H1 measured the neutrons instead of protons, and here's the reason. So one can easily show that in this diagram, only the transversely polarized photon can contribute this. This is just this is a technical reason, but one can show that. So the transversely polarized photon contains a transversely polarized vector. It is a two-dimensional vector in the xy plane. And so, but the cross-section is a scalar, so you need another transverse vector to construct indices. And naively, the only available vector is the transverse momentum transfer delta. So the amplitude is proportional to delta, and that's why d sigma dt goes to 0 like this, if you don't consider the spin effect. But theorists, on the other hand, suggested to excite proton, because if you excite the proton to the p wave, then there is a p wave wave function contains a transverse vector, which can be contracted with this polarization photon polarization vector. And that's why H1 people measure the neutron from the decay product of n star. But we don't have to do that actually, because if you remember, the proton is a spin 1/2 particle. And as I said, if the proton spin flips, then there is we get a transverse vector. And that's why we have this plateau. This cross-section is not vanishing as t goes to 0. So I suggest to look at the elastically scattered proton. This was not done at the H1 collaboration at HERA. At the EIC, we can do that. So we get d sigma dt non-zero at t goes to 0 without exciting proton. So that is our suggestion. All right, so this is just the details of the measurements and my comments. And it's not, I prepared this for maybe for the discussion session, but let me, we need a top EIC energy. One energy has to be as large as possible. And unfortunately, we don't have a prediction for the magnitude of the cross-section because we know nothing about the magnitude of the orderon. So that just has been worked out. And the theory, of course, theories are more comfortable with the Q square larger than 1 GeV, but I don't explain. Well, if you find this process that Q square equals to 0, that is still a signature of the orderon. And larger T is also interesting because in the larger T region, you are sensitive to the probably sensitive to the spin independent orderon. And as I said, there is a competition with the Primakov process, and the H1, according to the H1, they say this is negligible, but that actually depends on the cross section of the orderon. And there is a recent study by Adrian Tomek, well, they consider the Yetashi production. All right, so another things to consider is actually this process has been measured at the JLab, but much lower energy, where the emphasis there was the chiral odd quark GPD like H and E tilde And the main motivation was to study the tensor charge. So the final state is exactly the same, but energy is much, much lower. And in that case, the cross-section is given by the chiral clock GPD times this twist-free pattern distribution amplitude. And but as the energy increases, then this contribution should die out, and the Orderon takes over. So it's very interesting to see if we can see this transition from low energy to high energy at the EIC. That's another interesting thing to look at. All right, so I want to make a connection to the LHC Orderon, and this is a bit difficult because, of course, we don't have a theory of Orderons at LHC because there's no hard scale in the total cross section or the differential cross section at T very small. There's no hard scale, so a perturbative approach does not work. But nevertheless, let me try to make a connection between this G11 and G12. How do we see that in LHC experiment? So if you consider the forward proton-proton scattering, the elastic proton-proton scattering at LHC, there are actually 5 independent amplitudes in terms of helicities. So there is a helicity non-flip amplitude phi1, and single helicity flip amplitude phi5, and double helicity split amplitude phi2. And from general argument, we know how this amplitude behaves as t goes to 0. And most important thing for me is this phi2, which is a double helicity flip amplitude. And this is actually goes to constant if the t goes to 0. And that might be important, because if you calculate this elastic scattering cross section, d sigma dt, then you sum over all these helicity amplitude, because the measurement is inclusive about helicity. And so you have the usual low parameter, which is the ratio of real part to the imaginary part of the elastic scattering amplitude. But there is an additional term, which is proportional to this phi2, and that's coming from a double helicity flip amplitude, and that goes to constant. So it contributes to the d sigma dt at t equals to 0. And this is usually neglected, but this is where the spin-dependent Orderon comes into play. So so in this paper, we cooked up a model. We want to mimic this proton-proton scattering like a DIS. So we consider this PP scattering in an asymmetric frame, which is similar to the dipole frame. So one proton is very slow and the other proton is very fast. And in this frame, proton splits into the dipole, which is consisting of a quark and a scalar diquark. So this is a similar setup to DIS in the dipole frame. And in this frame, we calculate this helicity amplitude. We can calculate all of them. And here we only show this phi1 and phi2. And here in this phi1, you have this spin independent Orderon G11 here. And then there is a spin dependent Orderon in the phi2. And this is actually the leading term. So the phi2 is dominated by spin dependent Orderon in the t goes to 0 limit. So I said there are different types of Orderons, and they play an important role on a different region of t. So I think the LHC, the Orderon discovered at LHC is probably related to this G11, where t is non-zero, the deep region. But if you go to the t goes to 0, I think there might be some contribution from the spin-dependent Orderon, and which dominates this phi2. That might affect the extraction of the raw parameter according to this formula. All right, so here's the, in this paper, we also calculate the energy dependence because we know how the evolution equation satisfies this G11 and G12. So here's the energy dependence of the helicity flip amplitude and real and imaginary part. And as I said, if the energy increases, it is suppressed because of the saturation effect. But I don't know if the saturation effect is important or not at the LHC forward region. All right, so this is another slide for the discussion session. In fact, you can actually measure this helicity amplitude. This has to be measured actually at RIC. and also at lower energy. And so this phi 2 is proportional or roughly proportional to this the so-called double transverse spin asymmetry ANN that has been measured at RIC. There is a preliminary result from the SAR collaboration at 200 GeV. They fitted the data and they found very small value for this real part. And I don't know. I had a discussion with Vodic about this point, but I have some comment. I made some comment about the fitting procedure, but maybe this is for the discussion session. And on the other hand, as I said, this R2, if it's non-zero, can affect the extraction of the raw parameter. And so usually when people extract this raw parameter, they do this CNI analysis, the nuclear interference, and they assume this R2 is just zero because the spin flip is assumed to be zero. But I was wondering if one can generalize this procedure to include this spin flip amplitude in the CNI analysis. That's also an interesting point. All right, so let me come to the last part of my talk. That's this ordering in Adhdft. And as already mentioned by previous speakers, Adhdft is a correspondence between string theory in 10 dimensions and N equal 4 super Yang-Mills at front coupling limit. And as I pointed out by Chung-Yi and his collaborator, that Orderon in string theory is an antisymmetric B field in 10-dimensional supergravity. So this is a 2-index gauge field, so beta alpha beta, so B alpha beta, and this is, since we are in 10 dimension, this is a 10 by 10 matrices, and there is a diagonal term where the both indices are along the ADS direction, and there is the off diagonal term, which one of the indices is along the ADS direction, and the other index is along the S5 direction. And Chung-Yi studied this diagonal mode, and they found 2 families or 2 towers of orderons with these, and these are the intercepts that they find. And in this paper, we studied this off-diagonal mode, and we got a different tower. K is 0 and 1 and 2, and so on. But there is so what is more? Which one is the most important orderon? So as far as the value of the intercept goes, if you pick up this first orderon and set k equals to 0, then you get j equals to 1. So this looks like the most important orderon, and people often say that the orderon intercept is 1 to all orders in coupling, even at a strong coupling limit. But one has to be a bit careful because this leading orderon with j equals 1 is actually a gauge artifact. So as I said, the B field is a gauge field. You have a gauge degrees of freedom, and this j equals to 1 mode is just that. And there is no corresponding operator in super Yang-Mills theory. So this is usually in the Adhdft dictionary, this state does not exist. But according to Chung-Yi, they argued, Brower and Chung-Yi, they argue that this mode becomes physical after you do the analytic continuation in J or after you do the regularization. Okay, so that was a point Chung-Yi was making in previous talk. So in this paper, we also calculated the total cross-section difference in proton, or let's say the proton-proton scattering, or the baryon-baryon scattering. So in Adhdft, of course, the baryon is a tricky object to define it, but according to Witten, the baryon is a D-plane wrapping. And so this is a 6-dimensional object. This is actually, it's called a D5 plane. Wrapping on this 5 sphere. And so we have 2 D branes in this ADS5 and scatter them at very high energy and exchange the B field with the regularized B field, which is mimic the orderon effect. And in this calculation, we find that the leading orderon at j equals 1 decouples. And this is a point which Chung-Yi was objecting. He says the coupling is non-zero, but we could not show that. So if he can do that, that would be great. And so because in our case, the leading term decouples, we use the first subleading orderon, which has an intercept slightly less than 1. So 1 minus the order of 1 over a square term lambda, where lambda is the coupling. But we found something very interesting because we first calculated the amplitude impact parameter space, and if integrate over the B, then this effective intercept gets shifted. So we started from the intercept less than 1, but after the B integration, we get the intercept exactly equal to 1. And we also, so this is one thing, but more interesting thing is that a prediction is total cross-section in PP is larger than the total cross-section in PP bar. And that's something very counterintuitive because this is certainly not the case at low energy. At low energy, the PP bar cross-section is always larger than the PP cross-section, but this will be reversed at asymptotically high energy, and the difference is a constant in energy. And this might be counterintuitive, but I want to point out that this is actually in agreement with the very fast prediction by Lukashek and Nikolevsky in 19. So if you look at this very fast paper on Alderani, then they predict that. And I was very surprised when I found that out. So, okay, so let me summarize. So here's the take-home message. There are different types of orderons. In DIS, there are 3 orderons, both spin-dependent and spin-independent, and we can classify them using the generalized TMDs. And I think orderon fits perfectly with the scope of EIC because it is connected to small x and spin and tomography. These are the 3 pillars of the EIC science. And we took a fresh look at the exclusive Pizarro production with improved theory. So the cross-section is non-vanishing at t goes to 0, even without exciting protons. So that is something nobody has measured it yet because H1 collaboration measured something else. And I think this is complementary to the study of orderons at the LHC. So that's basically the end. Thank you very much.
Yeah, thank you very much for this very nice talk. And very nice. I think it's very interesting what you told us. Other questions, comments from the audience, please. Oh, the variants. So I go ahead. The first one was Oleg. So please, Oleg.
Thank you very much, Yoshitaka, for this interesting talk. Very interesting talk as usual. And I have a couple of questions. And the first question concerns the use of exploration of spin flip amplitude in non-polarized processes. And as you stressed, you don't need to have polarization, right? It's just orderon which selects the spin flip amplitude.
Right.
But my question is, suppose you have a polarized proton beam. When it seems, if you go again, instead of single pion to pion pair, without definite charge parity, you may have a Pomeroy-Orderon interference and single spin asymmetry. So this means if you study together the pion production, maybe raw production and interference, it's some complementary tests of Pomeroy in the Orderon square, if you have unpolarized beam and spin flip amplitude square, and maybe also interference. This is my first question. And second question is probably quite, well, maybe naive and not very well formulated about this inequality which you mentioned, this counterintuitive inequality in the end between PP and PP bar. Could it be somehow related, because you study ADS, to the comparison of energy momentum tensor and electromagnetic current? So you may have just interaction through through the current, the coupling, and to energy momentum tensor. And we know that, say, the gravitational radius, mass radius is much smaller than relation between to that.
Okay, so the first point, I couldn't agree more. I think this is what you're trying to do in this paper, right?
Yeah.
You consider this pion-pion production. And as I said, we can consider the spin effect. Here, well, this result is for the unpolarized cross-section, but we can polarize proton, right? And that's actually my next project. we just started this.
Yeah, very good, very good.
Okay, so
I think it's important to have complementary signal, right? So you may compare the and also, of course, as we stress in the interference, it's linear in Oderon, right?
Yes.
So polarization, the signal is linear in Oderon, not quadratic like and for this inequality.
Well, we will have to figure it out.
Somehow the property of energy momentum tensor in comparison to current, but maybe this is quite loose question.
Yeah, about the second point, this particular result, this is very unusual because we are scattering D branes, which has the same charge.
Yeah.
And usually, if you scatter same charge object, there is a repulsion, right? And the cross section is usually smaller in that case.
Yeah.
However, this is a very interesting point because the Adhdft space is curved. Because of the curvature of the space, this sign is flipped. This is very technical, but I was very surprised by this finding. So this is a this is a signature. This is a signature of the QCD is dual to a theory which is curved gravity space. So this sign flip is caused by the curvature of the ADS. That's very important, interesting result.
Okay. Thanks.
Okay, so there's now another question by Rodek, and then comes Chang-Tan. So Rodek, please.
Hello. So I have actually a quick comment to Yoshi on this pi zero production at Hera and then at the EIC. I will make a little bit advertisement here. So first of all, the reason H1 did not measure the proton in the forward direction is because they did not have Raman pots. You need Raman pots, a special equipment that measures forward protons, but they had forward neutron calorimeters which could measure the neutron. So it was just purely experimental setup which decided this particular thing. Yes,
but
this is not true.
Yeah, it's not true. H1 had a Raman pot.
Yeah, but for this measurement, were they used for this measurement? I know they had them. But
yeah, they had Raman pot, but the acceptance was not at log psi.
Correct.
So they had it higher psi.
Okay. So they couldn't use them if they had them. Now for the EIC, and maybe commenting on Oleg's suggestion, as you know, we're going to have polarized protons also. So we can measure something you're interested in and also something you're now calculating, which is the same process with polarized protons. So this is very interesting to follow as to what comes up.
Yeah,
and of course, there are Raman pots to measure the forward protons. So you have all the conditions you can dream of.
Yeah.
Very nice.
Okay, then finally, Chang-Tan, you should.
I have a question on your double spin flip amplitudes. Before I ask the question, I want to clarify a remark which I made. I actually do not disagree with you. The coupling has to vanish. Indeed,
sorry. So you want to talk about ADS?
Yes.
Okay.
The coupling has to vanish because we do not have a physical spin one massless state. So therefore, it vanishes. But in a string, a string dual approach, the Adhdft trajectory is a rigid trajectory. The contribution, it comes from a residual function times a signature factor over a pole. So this being a R signature, so a J equal to 1 is 1. It does not vanish, unlike the case of Palmer. So therefore, you have a residual function over T equal to 0. The vanishing of the residue precisely cancel the pole, so you are left with a finite contribution, but there's no physical particle at that point. So therefore, I completely agree with you. The residue has to vanish. Nevertheless, you will contribute to the high energy cross-section, total cross-section for PP and P bar P. Okay.
Yeah, So
Okay.
I want to comment on that first. So in this calculation, we worked in impact parameter space, right? And we have to integrate over P to get T equals to 0. So maybe we missed that.
Okay.
The T equal
Yeah, we can talk about that later. Okay. I think it's good. I'm glad to get a chance to clarify this point. But I do want to ask a question on your double spin flip.
Okay.
Based on my understanding of past experience working with spin, like a nuclear scattering, the spin flip amplitude usually vanish. But what people miss is that it actually does not vanish to higher order. That is, what happened is the residue vanish at a power of t or square root of t that kills the leading term. But the next order term, it does not vanish. So my question is, when you write down your double flip spin amplitude, it's assuming in the context of a Reggie exchange, shouldn't the power of S also be suppressed? Is that related to your suppression of your R factor?
No. So from general argument from symmetry, the rotational invariance, this double spin flip amplitude does not have to vanish, right? You agree with that? Right?
That's right. That's right. But the point is, when you now consider a Reggie exchange, what happens is the power is suppressed by 1 or 2 units, depending on the spin flip.
No, there is no energy suppression from this phi 2.
I know that's true for nuclear scattering.
Then what's your question then?
The question is, I'm asking you, when you consider this effect at LHC, should that contribution be further suppressed in energy?
No, I don't see that.
Okay.
Well, at least in this calculation.
Okay.
So maybe a question. Sorry that I cannot raise my hand as an organizer. So yeah, I was wondering if it's possible, in fact, to look for the other one is the proton-lead interaction, because you should be able to look, I mean, depending on the trigger, I mean, that's to study the trigger, but in pion production, since the photon comes from the lead, obviously, because I mean, to get exclusive pion production, and why I'm using lead is to get this photon interaction. I mean, so consider like a photon gluon collider for the LHC. So using lead allows me to consider a photon emission by the lead, and then the Pomeron on the side of the proton. And then we can check Pomeron and Oderon contribution via the pion production at the LHC. Do you think it could be a good idea, I mean, to look for this kind of events at the LHC?
Yeah, we are thinking about that.
Ah, okay.
I cannot say more.
Okay, that's good. Maybe we could discuss offline.
Yeah.
I have related question. What about the exclusivity?
On which process?
Yeah, that's what Christoph said, that you have this, because I understand it is coherent photon emitted from a lead. And how
Well, that's more like experimental questions, but this UPC is nowadays very popular, and it has been measured at LHC and the RIC, and I think they can do that.
Yes. Of course, I mean, we need to check the trigger, because they depend on the PT of the pion production. So there's something that we need to check, what would be the PT of that pion and where it is inside the detector to trigger on this event, because if not, it would be extremely clean. You have just pion production in proton lead, and this would be extremely clean event. So
is it forward production?
This is something that I mean, I need to discuss with Yoshi, because I have no feeling how it's what is the eta and the energy distribution of these pions.
Yeah, it should be a forward direction.
Yeah, but how forward and so on, and what is the energy? So it's something that we need to check. I mean, to trigger already on this kind of things. Yeah.
Okay, so maybe let's push the discussion out to discussion session in case we want to talk more about it. Let's go to the next talk because we are a bit behind now. So next talk is by Dmitry Melnikov on Oderon and glue bonds.
Hi, so thank you. Hi, everybody. I'd like first to thank all the organizers behind this event, and my connection is Christophe, so I'd like to thank him especially for giving me this opportunity. So I should start sharing my screen. So my talk was announced as a connection between orderons and globals, and I have to say that actually I will be discussing this mostly from the point of view of Adhdft correspondence, and we had already some results mentioned today in the talk by Leszek and also by Yoshi, and I look forward to the talk by Chun-Yi tomorrow. So my expertise is more in this connection with, well, globals and holography. So my presentations about connection to orderons will probably be a bit naive, so I apologize for that. And in fact, so this will be a review of somewhat not very new results, but the motivation to bring it again is the new developments in lattice theory, in calculations of string amplitudes, but also these experimental discoveries of the orderon that we're discussing today. So most of the results actually qualitatively was explained in the works of Chun-Yi and other collaborators. So let me start by reviewing that. So the old problem of string theory in flat space, or rather the first success of string theory in flat space was the explanation of the Regge behavior of the amplitudes in hadron scattering. And we can derive the Regge behavior from calculating string amplitudes. But the string amplitudes, they do not match particle amplitudes in other regimes. For example, elastic scattering at large angle, or scattering at large negative t, and so on. So, well, if we discuss So if we discuss this Regge behavior as the contribution of the exchange of Pomeron, then this is explained, there's a natural explanation of that in string theory. That is a simple tree-level amplitude in string theory in exchange of closed string between two string states, either open or closed, that represent the scattering hadrons. And the leading Regge trajectory is that of the graviton. And we also say that this is the Regge trajectory of the 2++ glue. And of course, string theory works, it's easier to work in the limit of large number of colors. And this is mostly the regime that I will be discussing today. So on the other hand, there is another discussion of Pomeron in the famous work by BFKL. So these are the exchange of Reggeized gluon states. So you can sum ladder diagrams in exchange of gluons between two scattering hadrons. And while this is valid in a different kinematic regime than that of string theory, in particular for large negative t rather than positive t. And so this is the so-called hard BFKL Pomeron. So one of the problems, one of the original problems, is how to connect the two Pomeron descriptions. And this was understood in the beginning of 2000, originally in the work by Plachinsky and Trussler, but also with contribution from Brouwer and Chun-Yi. So the idea is basically that instead of considering strings in flat space, so that string theory fails to explain other than Regge regimes, we should look at strings in curved space, like the one of anti-de Sitter space. And this fits naturally in the proposal of Maldacena of Adhdft correspondence. So in that sense, we should understand the string amplitudes rather as a dual description. So, for example, the exchange of a graviton in strings is not really an exchange that happens in the scattering of hadrons, but we have an exchange of spin to state, which is dual to the graviton from the point of view of Adhdft correspondence. So you can, as anticipated by Polchinski and Trussler, and then later the details were worked out in the work by Brauer, Polchinski, Trussler, and Tan. You can also, considering strings in curved space and empty de Sitter space, you can in fact also reach the BFKL regime. So if you're at large, coupling and large number of colors, this is again where string theory description works the best. You can get full analytical control on the amplitudes and discuss the results for the Pomeron exchange at any t. And interestingly, this has another connection with the BFKL Pomeron, especially the Maldaceno's conjecture and n equals to 4 supersymmetric Young-Mills. So this is a conformal theory, which is in some way similar to QCD. If you think of QCD as a theory which is approximately conformal at high energies, then n equals to 4 super Young-Mills can be a simple toy model where you can ignore effects of confinement. And this is where some of the ideas of BFKL has been tested, and currently there's some calculations up to next to leading order. Okay, so if we discuss the orderon, so there were several talks today by Tim and by Leszek explaining the basic theory behind that. So, well, we have behaviors. So we have two cross section of particle proton-proton and proton-antiproton scattering. They're expected to have different scaling exponents at large energies. So here in this, these are J0 plus and minus. And what is expected that the difference between J0 plus and J0 minus is positive and can be fitted from the experimental data. So that was related to the question that Chun-Yi asked a bit earlier to Tim, and I hope that there's some there's some analysis of data is going on to trying to extract this data. So if we want to understand how this C-odd exchange works in string theory, well, the idea is pretty straightforward. So if we discuss strings in certain background, there's a metric, but there is also in the Navier-Schwarz sector of string theory, there is a B field, the Karl-Bromont field that was mentioned today several times. So we expect that this coupling, the perturbations of the Karl-Bromont field is something that should produce this spin 1 charge conjugation odd exchange. So that was the basic idea from the point of view of Adhdft was discussed by the work of Brown, Jurich, and Tan. And here I copy the data from comparison of the exponents of the leading cuts in the J plane, computed in weak coupling and strong coupling. So, well, the difference in case of Pomeron, you have well, in strong coupling, you see that the cut is located at 2, and at weak coupling, the cut starts at 1. While for the Adhdft, you expect that both cuts are somewhere in perturbative regime, and in a strong coupling, they are both close to 1. So what effectively appears in the formula for the leading cut is the mass squared of the of the excitation in the gravity on the string side. And I will come back to this a little bit later. So you can reproduce the Regge trajectories by making analysis in the entity de Sitter space. So if you're considering a theory which is asymptotically conformal, you can think of some approximation to QCD. Then what you would see that you have Regge trajectories, discrete set of Regge trajectories. So if you're in fully conformal regime, that everything will be just continuum, you will not see any discrete spectrum. But if you introduce some effects of conformal symmetry breaking, so in the work of Chun-Yi and collaborators, they consider it the hard wall model, which I'll mention a little bit later. So in this case, you have a discrete spectrum, discrete set of Regge trajectories, which for small t and eventually for negative t, they tend to a continuum cut in the J plane. So what you can also do, you can introduce effects of running coupling. So the theory is not exactly asymptotically conformal. In this case, there will be no continuum in the lower half of the plane, and there will be a set of discrete trajectories for any t. Right. So just once again, how do we describe Odron in Adhdft? So one way to understand how stringy Odron can be coupled to gluons. So maybe one of the questions, so why you can think of stringy Odron as something which is made of gluons. So you can think about it in this way. So we can consider, this is again explained in the work by Chung-Yi and collaborators. So you can consider the Wilson line operator, Wilson loop operator, and the closed string couples to the Wilson loop operator. And then, so you can parameterize this Wilson loop by the coordinate sigma on the world sheet. So on the world sheet, this coordinate, the charge conjugation corresponds to changing the sign of sigma. So you can separate the Wilson loop into positive charge conjugation, positive and negative part, and they would consequently source the C positive and C negative string states, string exchange. So if you expand this operator, if you do apply perturbative expansion, that you will see that the leading C even state is the 2 gluon operator, and the leading C odd state is the 3 gluon operator. So then the Poimer and Odron propagators, they can be computed as the 2-point functions of the corresponding 2 gluon or 3 gluon operators. And this is something we can do in Adhdft, at least in the regime of strong coupling. So that's the idea. So so this is finishing my first part, is just to once again, the take-home message is that if you want to discuss Odron and you consider strings in ADS space, then in certain regime, in large coupling and large number of colors, you can get full analytical control on the Regge trajectories, and they are dominated by globals. So you can extend this to negative t and get connection between BFKL Pomeran and the Regge trajectories for soft Pomerans. So the question is, what's now? So are there any interesting predictions from given the recent discoveries and recent developments? So there were some interesting works that were today mentioned by Yoshi, and some work by Chung-Yi and team and collaborators, where they computed corrections, large lambda corrections, so you can try to extract some predictions from that. and probably match this to experimental data. So what I will discuss today is, let's say, my own connection to the story through the global spectrum. And I want to discuss maybe a slightly less known example of a holographic model, a slightly less used example of holographic model that gives a nice prediction for the global spectrum and perhaps can be used in the study of the orderance. So this is the Klebanov and Trussler model. Let me first mention some early results for globals. So so there's a lot of things going on in lattice calculations, and this is the very famous plot from Morningstar and Pearden paper, the 12 lightest globals in SU3 pure glue Young-Mills theory. So what was done more recently is different studies of this global spectrum. So what happens if you add quarks? What happens if you take the limit of large C? And also different couplings of these globals to hadrons are being studied on the lattice. So one nice thing about the globals that we learn from lattice calculation is that they are, at least the ground states, they are not so much sensitive to, for example, unquenching the theory or adding quarks to the pure glue theory. So here you can, in this table, you can compare for the two lightest states, 0++ and 2++, their ground states. The masses do not change very much if you add quarks, if you introduce the quarks in theory. It is a bit more subtle for 0- state. This is a special state, so here one should be a bit more careful. And the result is not so nice. A 1± state, that would be something that a candidate for the orderant. The situation is still good. Yeah, one of the parameters which I use to estimate the quality of my results is the ratio of the 2++ and 0++ states, which for lattice in SU3 case is about 1.4. So the second good thing is that if you try to crank the rank of the gauge group, the results for the globals, the mass for the spectrum of the globals is not very sensitive. They're stable, and we can easily expect that in the large NC limit, we can get sensible results using holography. So here, just again, the lattice results where you can see how the masses vary if you change the rank of the SU group and also SP group. And the parameter, which again I want to look at, is the ratio of the two masses, which is a more clean measure of the spectrum. So it's again stays somewhere close to 1.4 in all cases. So if we move to holography, well, there's a simple way how you can try to estimate the spectrum of globals. The most simple idea is to look at this hard wall model that I mentioned earlier in relation to the work of Chun-Yi and collaborators. So you basically consider just the regular theory supergravity in anti-de Sitter space. This means that your theory is conformal, but then you can break this conformality by introducing a scale. So you put the boundary condition at some value or at some position in your space. So this is a hard wall. You just study the theory bounded by this hard wall. So, and you can study, for example, a Schrodinger equation for particle of spin L in this geometry. And then you would actually, well, it's an easy problem. You can get the spectrum, and in some, as I will mention a little bit later, so in some sense, this already gives a nice prediction. So this is connected. This kind of analysis can be generalized in the work of Chun-Yi and collaborators. They were deriving this kind of equations more honestly in ADS5 cross S5 theory. And if you want to, for example, study rigid trajectories, you need to modify slightly the equations. So you need to consider the next order in coupling constant in lambda. And this is how you modify your equation and solving this equation. So here Jn is the eigenvalue and t is the parameter. So you can find Jn as a function of t, and this will give you the rigid trajectories that we have seen before. So what about the global spectrum? Well, there's another model which is slightly better motivated, called Witten's model. Well, this is basically taking some, this is analog of ADS5 crosses 5, except that you start from D4 branes instead of D3 branes in type 2A. But you want to get something which is not conformal, so you introduce a scale by compactifying this theory on a circle. So this introduces a scale, it breaks in supersymmetry and conformal theory. And Brouwer, Tan, and Matur, they were pioneers in studying global spectrum and holography, and this is the spectrum that they got. Very reasonable, especially if this is one of the first derivations, is to see many familiar states. The only problem in this particular theory, well, there are two problems. One is that you get very high degeneracy, basically because you have this symmetric factor space and you have additional symmetries. So your global states, they actually degenerate. And also somehow it happens that in this model, I'm not sure what the reason is, but you get higher gaps between the states, between the masses of the global states. So you can see, for example, here, comparison of this BMT model with lattice data at large in C. And you can see that, well, if you normalize everything to the lightest state, then the masses would start to diverge quite rapidly. And these last two tables, they're just the estimates in the very naive model. As I said, let's consider just the simple Schrodinger equation into the Sitter space. Well, nice feature of this model that you get very nice ratio of M2++ and M0++, which is again around 1.4. While for the Witten's model, you get something like 1.7. All right, so now I want to briefly introduce the Klebanov and Trussler model. So that's one model which is neither ADS, neither CFT. So it's a supergravity in the space which does not have conformal isometries of anti-de space. So the metric explicitly break this symmetry. And so the dual theory is for example, is a gauge theory, but with a running coupling constant, which makes it a very interesting example. It's quite a rich theory. It has also large global symmetry. It is n = 1 supersymmetric, which is good if you want to study maybe some physics beyond standard model. If you want to focus on QCD, this is not so good. So let's see what this theory gives us. So you can study, for example, you can start by studying globals in this theory. And what is expected that in infrared, this theory flows to SUM Young-Mills with some additional symmetries and some additional fields. In particular, there'll be some few massless particles. I will show the spectrum a little bit later. So this is just to mention contributions to this study of the spectrum. And in this study, I'm focusing just on a subset of states that would appear in supersymmetric Young-Mills or in the just non-supersymmetric Young-Mills. So I just want to project out all the states that do not exist in the original theory. So in particular, the C-odd sector was studied in the work by Bena, Demarsky, Klebanov, and Solovyov, and also in my work with Demarsky and Solovyov. And the summary can be found in the proceedings of the Low X meeting in 2013 and my work with Ivan Gordelli. So somehow I was recently revisiting these results and comparing this with lattice calculation. So this is the full spectrum of the super Young-Mills sector. You have many different globals, and here you can see them with excited states, and also the different supersymmetric multiplets. So every state comes with a bosonic super partner if it's a massive state. So if you want to discuss non-supersymmetric sector, you have to basically throw away half of the states here. There's a pair of massless states. which is connected to the spontaneous breaking of baryonic symmetry. So here, so throwing away lots of states. So here I just do comparison in this plot with the lattice data. And on the right-hand side, we have C odd sector, where the gravity calculation shows 4 states, and one has to be dropped if we would discuss a non-supersymmetric. So 0 minus global is not there in the original super-Young-Mills, but 1 plus minus, 1 minus minus, and 0 plus minus are there. And you can see, comparing them with SU3, that they give very, very good match masses. Well, similar story happens in the C even sector. I think there's a nice match. I summarize it here. So if you look at the second table here, this is just, I look at this ratios of 2 plus plus and 0 plus plus for 6 lattice globals. So 2 plus plus is not interesting because I normalize it everything by the mass of 2 plus plus. But this is just comparison with SU3. I do not have all the data for SU infinity. So for SU3, we typically it's less than 10% accuracy. I'm just discussing the ground state because if you look at the excited states, they do not fit so well. So for different reasons. So concluding, so how this could be useful for Orderon. So global states, they are certain intercepts of the Regge trajectories. So there was a discussion here of what is the Orderon, how do you get it in the DSCFT, and in fact, apart from Karl-Bramon BMN field, you also can perturb the Ramon-Ramon's 2 form in type 2B theory, and this will produce the 2 perturbations of 2 fields will produce in this Klebanov-Trussler theory. Once you mod out, once you project out all non-super Young-Mills states or non even Young-Mills states, then you would get just 2 spin 1 states, 1 plus minus and 1 minus minus, exactly what is seen in the lattice calculation. And this is the prediction, let's say, from the holographic model of the ratio of the masses of this, let's call it Orderons to Pomerans. So one thing that can be done, and I'm not sure that was done, is to do this analysis of Brouwer and collaborators to extend to find the Regge trajectories and to find the position of the intercepts. So well, to say more about the masses of the states, so there is in terms of ADS mass, they have mass squared equal to 15. So they would, and dimension you can derive using the standard Adhdft dictionary. You can see that this is mass squared equal to 15 corresponds to dimension 6 operator. So it means that these globals are created by these cubic combinations of fields F mu nu. And in this theory, as I said, so Klebanov-Trussler theory, this is a theory that has logarithmic running of coupling constants. So here, in fact, this is not the full dimensions, there are anomalous dimensions, and the 2 operators, in fact, mix in this theory, and this information you can also extract from the gravity calculation. There's no massless state, so this is something that was discussed today several times. There's no massless state. Maybe we will come back to the discussion of this a bit in the end of the day. Okay, so this is my conclusions. So first I was trying to convene that string theory is a tool that allows to have a unified picture of high energy scattering of Pomerans and Orderons. So far in the leading regime, and it would be interesting to make quantitative predictions. I'm not sure exactly how much was done in this. I mentioned one work by team and Chuni collaborators. So one can try to get prediction about leading cuts and leading intercepts. And also, so I would like to bring attention to Klebanov-Trussler theory as a very interesting holographic model. It is a bit more complicated to study. So if we, for example, discuss the approach of Yoshi and coupling globals to baryons, I think this should be quite a nightmare in this theory, but probably still possible. So yeah, so I think I want to end with this question. So whether indeed we can go further and make nice prediction and make connections with the experiments and recent experiments on Adhdft. Thank you very much.
Yes, thank you very much for this interesting talk. Are there any questions, comments from the audience? Please, Chang.
Okay, that's a very nice talk. And in fact, I learned a lot. I do have a question regarding the Klebanov-Trussler model. One of the problem with lattice calculation is the unique feature that there's the lattice global 0++ relative to other states. In most models of Adhdft, a simple-minded model, for instance, in the hard wall model, you will find that 0++ is actually degenerate with 2++. Now, when we work with using the Wigner model, one of the surprising things we found is indeed we got a lattice 0++ global. In fact, we claimed that to be a triumph of the model. So my question is, in the Trussler, Klebanov-Trussler model, does the degeneracy between 2++ and 0++, that degeneracy is gone? And do you get a light? You may have shown that, I just missed it. Is that your 0++ is much lighter than 2++?
Yeah, thank you very much for this question. So indeed, so this is the plot from your work.
Yes.
And there is a light 0++, which is not degenerate, but as you point out, it does not come from perturbation of the dilaton. And the dilaton is the field that we expect to be dual to trace F². So although there's 0++, it's probably not the right one. So if you go to Klebanov and Trussler, so what happens in this model that 0++ and 2++ and also 1++, they all but in Klebanov-Trussler, it seems to be solved. So I didn't discuss this in my talk. I just flashed the table here. So if you look, well, the scalar sector is also quite complicated. So you have 6 or 7, depending on how you write the equations, coupled differential equations, and which is quite difficult to solve numerically. And you see 7 towers of scalar fields, which you need somehow to disentangle. So there is no degeneracy with 2++. That is for sure. The question is like, what is the lightest one? And I think so. This is also partially the work that we've done recently with my student Cornelio. So we tried to study the spectrum of pseudoscalars in this model, and we sort of argue that the lightest is lambda lambda. So that's in supersymmetric. If we just talking about just pure Yang-Mills, it is not there, so we should ignore it. So the correct one, 0++, is this one, and there are indications that that's the right one. That's the one that couples. Well, again, everything couples in this case. The dilaton perturbation couples to 5 other modes. So it is a bit inconclusive in that sense, but let's say I hope that we will be able to somehow get the final answer to that a bit later.
Good, very good. Thank you.
Thank you very much. Then I think we should go on.
I have one short question. I cannot raise my hand as usual. So, yeah,
go ahead, please.
I have just a short question about what we discussed yesterday. I mean, you may remember that we discussed, I mean, it's kind of hotspots of gluons inside the protons, or I mean, that maybe some local high density gluon inside the proton that may lead to saturation and so on. So I was wondering if there is not a link, I mean, between this and also the glue balls, or also, I mean, Pomeron and Oderon, because they, of course, I mean, in that case, you can get the, if you have odd or even number of gluons, again, the diffractive events that are explained by this kind of hotspot that might appear in the protons. So related to this kind of CGC, basically, model. So I don't know if there is a link, there could be a link between your calculation and to explain this kind of hotspot in the proton.
Well, unfortunately, I had to miss the most of the day yesterday, so I cannot really comment on that. So maybe a little bit on connection with glue balls. I think if you adopt and accept the string theory picture, then yes, the glue balls. Well, the glue ball rigid trajectories, they are the Pomerans and Oderons. So
yes, yeah.
The main problem is to be able to extrapolate these results from large coupling to some reasonable regime, and we'll see if this somehow can be matched with experiment.
Right. Thank you. Yeah.
One thing that can be tried also is coupling these glue balls in holographic models to baryons. So that was, in fact, Yoshi mentioned that. And, but the baryons, my point of view, they're quite complicated. So the analysis is not so easy. And well, I cannot say much about the prediction of Yoshi, but I think, well, in my experience with baryons, that they do give some unexpected predictions.
Okay, I think then can be done. No? So, okay. So again, thanks a lot for this very nice presentation, and we go now to the next speaker. That is Giovanni Chirilli, and we're also going to switch now, I think, a bit away from the Oderon topic to different aspects, and it's on the role of light ray operators in high energy QCD. So whenever you're ready, Giovanni, please share.
Yes.
Nilo's great. Nice.
Is it okay?
Yeah, very good.
All right. So thank you for the opportunity to talk here. I will talk today about the role of light rate operators in high energy QCD. I've been giving talks recently on the behavior of low X passive PDF, and also on a spin structure function, G1 structure function to low X. But I never mentioned the second half, the second part of the story, which is the role of the light rate operator. So this time I will try to, so to say, start from the end of the story, and then consider as an application the behavior of low X PDF and the spin structure function comparison with the three-loop splitting function. So this work is based. This talk is based on these two work which have been recently published, and in a third one which is in preparation. So we know that the scale dependence of the S structure function can be obtained by considering the twist to gluon operator, for example, if we consider gluon. And if we consider now the dipole DIS cross section, we know that this can be written as a convolution of the Pomeroy intercept, or if you wish, the impact factor. And then we have the energy dependence, which is given by the exponentiation of the Pomeroy intercept. Now, suppose that we consider the end moment of this structure function, then we are left with an integration over this parameter gamma. So to perform this integration over gamma, we have to go in what is called the unphysical point. In
to be specific, what is a physical point is the point where we have the singularity of the anomalous dimension in the mailing space. So to complete the integration and to perform the integration over the residue, we need to consider analytic continuation, and we need to make the identification that the parameter n becomes a complex value continuous variable. And then we take the residue, expand for small gamma, and then we invert this equation, and then we can finally get the analytic continuation of the anomalous dimension at the physical point for this twist 2 gluon operator. So the procedure that I presented, actually, it does not tell you what is exactly the operator which allows you to perform this analytic continuation. As we know, this procedure has been done at leading order or also at next leading order when Fadin Lipatov in QCD predicted the next to next leading order splitting function for DGLAP. So actually, if we consider the analytic continuation of the local operator itself, then we get a light rate operator, which is defined here on the right-hand side. So this is the object that whose evolution gives directly the anomalous dimension in the unphysical point. Originally, this non-local operator or light rate operators appeared in the work by Baliski and Brown when they extended the local operator product expansion in terms of light rate operators. Since then, there have been a lot of work, and for example, recently, there's been a work in calculating the 2-point function in the BFK limit, and also in the triple range limit. And a lot of activity in conformal field theory on a light rate operator is also present. And here I give just one example of paper, which is the seminal paper on this activity in conformal field theory. So actually, for what we need the full supermultiplet of local operators. And for simplicity, we work in n equal to 4 super Young-Mills theory. So if we consider the set of supermultiplet operators, so besides the gluon operator, we consider gluino and scalar. Then out of this operator, we can construct a multiplicative renormalizable operator S1, S2, S3. And the anomalous dimension are given here on the bottom of the slide. Out of this local operator, we can construct in a similar way the analytic continuation of the full supermultiplet. And after we have performed this analytic continuation, we construct for the forward matrix element this multiplicative renormalizable right rate operator S1, S2, S3. So notice that here this S calligraphic is actually different from the S which I was talking at the beginning for local operator. Indeed, the coefficient for this system is different. Now we consider, I'm going to motivate soon why we are talking about these multiplicative renormalizable operators. For example, if we consider the correlation function at high energy of the gluon operator, so instead of considering just the twist 2 operator, we consider a correlation function of 2 twist 2 operator in with this light rate operator. It turns out that when we consider the high energy limit, which is j goes to 1, as we understand now, is this going in this unphysical point, then out of this distance, only S1 operator is relevant because the other one will be neglected. And moreover, we know from conformal field theory that the correlation function of these the correlation function of 2 of these operators as a general structure, which is given here in terms of this unknown structure function. And then we have parameters like delta, which is the canonical dimension plus the anomalous dimension. Gamma A is usually given the meaning of anomalous dimension. And the goal is to calculate this structure function. Well, at least in the BFK limit, because to calculate in the complete limit is quite difficult. So to calculate this correlation function in the BFK limit, there is a difficulty which is given by the fact that this correlation function of this type are UV divergent in the BFK limit. So what one does is to calculate the correlation function of point splitting. So the point splitting can be of two types, Wilson frame or quasi-PDF frame. So in the Wilson frame, you can see here on the bottom of the slide, the first diagram. It's like you take this this bullet, which was originally on the bottom, you split and give it a transverse distance between these 2 points. So this type of gauge structure should remind us the dipole in DIS. So when we consider object like FJ with point X and point Y, we should keep in mind the similar calculation that one does with the dipole scattering for in high energy with the Pomeron exchanger in this rapidity gap. So this was the work done by Walitsky and collaborators. And the motivation was to give an example of real calculation for this structure function. And of course, the final goal is quite ambitious, and it is to understand the full dynamics of n equal to 4 sub-Young bills. In my case, it was the motivation was to understand and check the calculation by comparing the result with what is expected in conformal field theory general result, which I mean to compare with this result. But this time, instead of considering the Wilson frame, I would consider the quasi-PDF frame. And I will explain in a minute why this is the quasi-PDF frame. And in my case, the goal is to calculate the behavior of quasi-PDF at small x. So let's see the first application then, which is the quasi-PDF at small x. Okay, before we move there, yes, I did the calculation using this quasi-PDF. And indeed, the result coincide with the expected result in a conformal field theory. Here we have that the infrared cutoff mu in the general conformal field theory is given by this delta prime, which is the difference between x and y and x prime y prime. This result perfectly agree with the one also obtained using the Wilson frame. So once once I did this kind of sanity check that the Wilson frame calculation is working, then I use this result to consider the behavior of the quasi-PDF. So in 2013, Xiandongji suggested a way to calculate the Parton distribution on the lattice. And this was by considering space-like, bilocal operator with the space-like separation. Here we have the gluon quasi-PDF and the quark quasi-PDF. Since then, there was a lot of activity and a short list of paper is given here. So our goal is to find the behavior of this object, at least here I will present for the gluon, in the saddle point approximation, then compare this result in the leading twist approximation. So to calculate the leading twist approximation, we understand now that we need this light rate operator, which give us the analytic continuation to the unphysical point. So the technique to do this calculation is the one which one adopt also in GIS calculation. So if we have the T product of two electromagnetic current, this in a diagonal approximation is given as a convolution of the impact factor and the trace of two Wilson lines. Then if one wants to calculate this structure function, then one has to calculate the leading order impact factor, calculate the evolution of the relevant matrix element. We will work in the linear case, therefore it will be just BFKL. Then one use a model to consider the initial condition, and then convolute the solution with the impact factor. In our case, the impact factor is a different form. This dashed line is the quasi-PDF gauge link. And this is for us what is our operator. Now, if we want to follow this strategy, we have to calculate first the impact factor, understand what is this matrix element, and then calculate the evolution of this matrix element, which we know is BFKL, and then convolute it with the initial condition with the impact factor. So the challenge actually will be to calculate this impact factor, because here this point, Z1, actually is not a fixed point, but has to be parameterized, and then it has to run from X to Y. The calculation is done entirely in a coordinate space. So if we recall the GIS at high energy, we know that the virtuality of the photon is fixed. The center of mass gamma star proton gets very large, and X Bjorken goes to 0. The translation of these kinematics in a coordinate space is as follows. The transverse distance is fixed, while the longitudinal X plus and Y plus are kept very large. It was understood also that the proper evolution parameter working in a conformal field theory, it is this ratio between X plus Y plus and X minus Y perp, which is quite reasonable considering the X Bjorken in a momentum space. So, as I mentioned, I will not go to the details of the calculation, but I will just present the result for the quasi-PDF here in the saddle point approximation. You see that we have the usual Pomeranian intercept in the saddle point approximation, and we have this evolution parameter, which is the log of this x dot p, and here the mass of the nucleon and the absolute value of the coordinates x. Here we are working in space-like direction. So once this calculation is done, we have to consider the same calculation in the leading twist approximation. And here I present directly the result. Actually, there are two results considering two regions of this combination of the saturation scale and the transverse distance. So this transverse distance is just x. And this can either be between 0 and 1, and this is relevant for GIS case, which is what we are interested in. But if one consider the case where QSX is greater than 1, which is the evaluation of unitarity region, then one obtain a J1 Bessel function. Here, instead, we obtain the modified Bessel function. So the goal was to compare these two results. And here I plot this comparison. We see that when we go to small x, the leading residue is quite a different behavior at small x, which means large rapidity, than the saddle point approximation behavior. And the meaning of this is that the higher twist in this calculation of quasi-PDF cannot be neglected, but must be considered, because at a small x, the full BFKL dynamics is captured by the saddle point approximation. And we see that there is a quite different behavior. This is the first part of the talk and the first application of the light rate operator. As I mentioned before, the light rate operator was needed to calculate this leading residue result. Now, the second part of the talk, I will discuss the work on the behavior of the spin structure function at low x, in particular the one for G1 structure function. And the way to proceed is to extend the high energy OP result, which I presented in the first part of the talk, by including subiconal correction. So properties of this impact factor is that it is gauge invariant and it is also Mobius invariant. So if we consider deviation from the iconal approximation, then we would like to preserve this symmetry. So if we want to extend this high energy OPE and to include subiconal correction, then we have to consider contribution in the quark propagator by these two operators here. So all of the calculation performed, most of the calculation performed in high energy QCD are performed in the iconal approximation, which is given by this part of the diagram, which is the diagonal approximation. It's this Wilson line. On the other hand, if we consider deviation from this Wilson line, we have to consider new operator. And the full quark operator, with a subiconal correction can be found in the paper which I published in 2019 and 2021. But recently, in this last paper, I showed that the only terms which are relevant to study G1 structure function are this operator F, which is the semi-infinite Wilson line with the insertion of this Fij operator in the transverse component, and the quark operator, which is defined here. To give a better understanding, this is a visualization of these two operators. This is the quark operator, which can be rewritten using Fierce identity as a sum of these two operators. So out of this of two operators, we have to repeat the high energy OP steps. And this starts with the calculation of the impact factor. So considering the quark insertion in this quark operator, quark propagator, we obtain two impact factors. Indeed, one impact factor is relevant for unpolarized structure functions which are suppressed by energy. As we know, when we consider gluon ladder in a BFKL, we usually don't consider the quark loop because they are suppressed by power of 1/s. And indeed, if we consider subiconal correction, then we start to consider also this unpolarized quark contribution. On the other hand, the polarized contributions are genuinely energy suppressed. And here is indicated by this impact factor, which is given by the explicit expression is given in this slide. Besides this quark insertion, we have to include also the Fij insertion. And it turns out that this impact factor is exactly equal and opposite in sign of this the impact factor obtained with the quark operator. This should not be surprising. And the full OPE with this quark, with this subiconal contribution is presented here. We have the usual leading order impact factor and trace of two Wilson line for the unpolarized and iconal contribution. And then we have the contribution that is due to the subiconal correction. This I Q5 impact factor is the one which will be relevant for G1 structure function, and the evolution of this operator is the one that one has to calculate to obtain the behavior of this structure function at low x. So in this same paper, I have shown that this impact factor satisfies again the same symmetry. This was nice to obtain, so gauge invariance and the Mobius invariance. The structure of the new operator are given here. This rectangle is just the dipole contribution diagonal approximation. And on the bottom, we have the two new operator of which we have to calculate the evolution equation. So I will not go through the detail of all the evolution equation, but I will just mention that this operator here can be split in a sum of two operators, and then one has to consider the evolution of these two operators besides the Fij type of operator. So if we write this OP in terms of this new operator, which I was showing here on the bottom, then the OP for T product of two electromagnetic currents up to subical correction is presented here. So with this operator, we can construct a matrix element and obtain a new quark distribution, which I present here, and a gluon distribution. Some of the diagram for the evolution equation of this operator are presented here. As I was mentioning before, this Q1 is related to the unpolarized structure function, and this Q5 are related to the polarized structure function. Then we have also this operator, and again we have Q1 structure function and Q5 structure function. Q1, yes, unpolarized structure function which are suppressed by energy, and the polarized one. And then we have also the one with the Fij insertion, which can be quantum in the background field method. One has to consider background field and classical field. One has to split everything and then obtain this type of diagram, where here we have the gluon, which is quantum with the Fij insertion or with the quark insertion. And the evolution equation is presented here. So I want just to mention that here one has to take care of the parity of the operators. Here on the left, we have an odd parity operator. On the right-hand side, we have a parity even operator, but is multiplied by a tensor structure, so the parity is conserved. And here instead we have the parity odd operator. Similarly, if we consider the full evolution equation for this Fij operator, then the evolution equation is here. So the work of this paper include also the quark to gluon diagrams, and these are a new type of diagram which are presented here. And these are the evolution equation for unpolarized structure function and for polarized structure function. And then we have also the quark to gluon diagrams for these operators for unpolarized again and for polarized structure function. So in this evolution equation appears a new operator, which I call here Xi1 and Xi1, which means for unpolarized and polarized respectively. And this new dipole type of operator is never appeared in small x physics at least. But besides this new operator, there are also the usual TMD operator which appears in Sidis and Drelian. Okay, so my point was not merely to go in the detail of this calculation, but rather to mention that if we want to study properly the low x behavior of G1 structure function, with the Wilson line. Eventually, we would like to compare with what is known, meaning that we would like to compare with the anomalous dimension of this three-loop splitting function calculated by Mock, Vermaseren, and Vogt in 2014. And as I, using the technique that I presented at the beginning of the presentation, this is possible using these light rate operators. Of course, there is not a direct application because what I presented at the beginning, it was relevant for polarized case. And the work that one has to do is to extend this unpolarized supermultiplet to the polarized case. And this is a work in progress. Okay, so this brings to the conclusions. My first conclusion is that the light rate operators are simply analytic continuation of local operator to the physical point. And this gives the opportunity to study, for example, the low X behavior of quasi-PDF and obtaining the leading twist behavior of this object in the physical point, which means considering the leading twist approximation. Then, as I mentioned just now, before the conclusion, these light rate operators are important if we want to make comparison with a known calculation of the three-loop splitting function. And this is a conclusion regarding merely the spin structure function at low X. Now there are a new impact factor which were not known before, and a new evolution equation with the new quark and gluon distribution. And the relation of this distribution with the non-distribution is still unknown. As an outlook, one has to understand that the evolution equation that I presented are not merely in an evolution equation form. It is known that for the polarized case, when we go to low X, there are double log contribution, which has to be disentangled for the pure single log contribution. And moreover, there are original work in this direction done by Bartels, Ermolai, and Riskin, and Bussari, Hatta, Yuan have extended this in the case of orbital angular momentum. So of course, one has to compare after this disentangle between double log and single log is done. One has to compare with the NLO calculation by Mock and collaborators. A lot of work has been done in this direction also by Kovchekov's group, so kind of comparison with their result is mandatory. Eventually, one would like to include a next leading order contribution, and in particular, the running coupling correction. Since there has been quite a lot of discussion in this section about the order intercept, I could have given a full talk on the order in terms of this light rate operator, but I would just mention that one can calculate the scale dependence of this orderon operator, which is actually a twist tree operator, and using the spinor formalism, and then using this light rate operator, one can calculate this scale dependence of the order intercept. But this would have been a full new talk, and since the time is limited, I just leave in case people have a question. Thank you.
Thank you very much, Giovanni, for this very, very comprehensive talk. Other questions, comments? By Yoshitaka, please, Yoshi.
Yes, concerning this comparison with NNLO anomalous dimension, of course, Yuri worked a lot on that, but he was able to reproduce only one component. He only talk about the next leading order and only one component of the 2x2 matrix, and only in the large NC limit, I think.
Yes, but he was.
So your approach is better suited for that?
I think so, because what he's doing is he compared with Bartels and Molaev and Rishkin, and he compared all in the large NC. If you want to compare with the full three-loop splitting function, then one has to consider one has to fully consider the T product of two electromagnetic currents like Mock, Vermaseren, and Vogt does, but from the from the BFKL side, or if you wish, from the small x side. And the proper way to do this is first to calculate the evolution equation, and then one has to consider these light rate operators, and then you can start to go in the physical point and single out the double log and the single log, because Mock, Vermaseren, and Vogt in their paper, they have this single log and double log contribution.
Yeah, I understand, but even the double log is difficult, right?
Yes, I agree. Even the double log is difficult. That's why the work is in progress. But I want to mention that my evolution equation, which, as you see, they are also new terms. Some of the pieces that should have been reproduced by Yuri, there are some terms in which we actually kind of disagree, and they can bring some differences. But the main point is that I want to emphasize here that the approach is literally to go to the the fundamental of OPE, which means here considering. Oops, too much. I'm still sharing, right?
Yes. Yes.
So you see, the main point is to start from here, okay? So if you don't consider the T matrix of two electromagnetic current as it is done from, so to say, Diglap formalism, then it's difficult to understand how you can find an agreement. I mean, how do you compare, right? For example, in the unpolarized case, in the leading log, in the leading log order, one has this super multiplet, and one can consider the multiplicity renormalizable super multiplet, which is diagonalized. So there is a full formalism that can help you. And if and as I showed here, you can rewrite this local operator of renormalizable multiplicity renormalizable operator in terms of this analytic continuation light rate operators, which is what I was showing here in this slide. Mm-hmm. So you see, there is a formalism that will help you to find this, to make this comparison. So the comparison is the level of cross section. That's what I'm trying to understand, to emphasize. The impact factor that I have calculated, they are new. And if you don't make a comparison at the level of cross section, you cannot match with the this three loop splitting function.
Okay, thank you.
Another question by Pietro, please.
Hi.
Hi.
I have a question about this. I am not sure which slide was that. So there was this Wilson line frame, and then this corresponds to this the thing that you call the quasi-PDF frame. So, but then if you, let's say if you have some other gauge structure on this, in this quasi-PDF picture, to what kind of gauge link would that correspond if you have something else than that?
So the idea is the following. I'm not sure I fully understood. I mean, you can consider, of course, any type of gauge link here, right?
Yes.
But the point is the following. It turns out that to make a calculation of the BFK limit of this correlation function, one has to use this splitting technique, meaning that you have to split this from the light cone, you have to have a transverse distance. Yeah. So this is, as I said, similar to a dipole frame. This quasi-PDF is just a straight line, not because of my invention, although this is the most intuitive one, but actually it turns out to be more difficult one. It comes from a suggestion by G, which said that if you consider this operator with the space-like separation, now imagine that this space-like is between 0 and the third component, like here, and this x is also 0 and x third component. Now, when you consider this object with is not really on the light cone, but it is a generic point x. So it is literally this type of gauge link. This corresponds to quasi-PDF, not because I wanted to call in this way, but it really because it coincides with the Xiandong-Ji suggestion. Okay, and then I used the fact that this quasi-PDF is just a different gauge link geometry than the Wilson frame. And for me, it was a starting point because I wanted first to reproduce known result, and then to make sure that I understand what I'm doing to compare this saddle point approximation with the leading twist approximation. And that's why I wanted to understand what is this light rate operator, which is analytic continuation, and so on. So it was kind of a chain of arguments. But this is not my invention. This quasi-PDF has a physical meaning in at least in lattice. You can consider a different gauge. You could do the calculation, but to what it corresponds, I don't know.
Okay, okay. Thank you. Thank you.
You're welcome.
Okay, thanks a lot.
Thank you.
Then I think we go to the next talk now because we're pretty much behind in the timetable. So again, thanks a lot, Giovanni. The next talk is by Gianni Bentala, and he will talk about the recent coordinate calculations of exclusive vector measurement production at the NLO accuracy. Please, you're sharing, so great.
Okay, so hi everyone. So I'm going to talk about these next to leading order corrections, the longitudinal exclusive heavy vector measurement production. And this is based on this article I wrote with Heikki. So we are looking at this in deep inelastic scattering. So we have a virtual photon and a nucleus interacting. And then in the end, we get a single vector meson out. And we are considering heavy vector mesons, so Psi or Epsilon, for example. And this process is such that the polarization mixing is highly suppressed, so that it is very likely that the photon and meson have the same polarization, so either the longitudinal or transverse. And yesterday, Farid gave an interesting talk about this polarization mixing case. But in our case, we are going to consider the case where the polarization stays the same. So we are going to consider Psi production in the longitudinal polarization. And let me remind you that this process is interesting because here we can actually measure the moment of transfer. So via Fourier transform, we can actually probe the spatial structure of the nucleus. And we are doing this calculation in the dipole picture. So at the leading order, we can describe the process like this, so that we have a virtual photon that splits into a quark antiquark pair. The quark antiquark dipole then interacts with the nucleus and then forms the vector meson. At next to leading order, we also get Feynman diagrams like this, so that the quark may emit a gluon, and then this quark antiquark gluon system interacts with the nucleus. And we can write the corresponding production amplitude in this form. So here the first and second row correspond to the figures here. And basically we need three things to calculate this. So we need the photon and meson wave functions, and then the dipole amplitude, which tells us about the interaction of the dipole with the nucleus. And we are doing this calculation in this mixed space of coordinates. So in the transverse plane, we are using these transverse position coordinates, whereas in the longitudinal direction, we use this momentum fraction z. And this is useful because in the iconal approximation, the transverse coordinates of the particles do not change in this interaction with the nucleus. So first of all, we need the photon wave function, and this can be calculated using perturbative QCD. And this was done at next to leading order very recently by Guillaume, Thomas, and Risto. Then we need this dipole amplitude, and for it we have these evolution equations describing its energy dependence. So basically the Valsky-Kovtchekov equation. Then we also need the initial condition for the Valsky-Kovtchekov equation, and this can be taken from a fit to Hera structure function data, for example. And I'd like to mention that here we are only considering the t equals 0 case, because to get the t dependence, we would need an impact parameter dependent dipole amplitude, and that would require additional modeling that we don't want to do here. And then finally, we need these meson wave functions, and these are unfortunately non-perturbative. So what we can do to get these meson wave functions that we need is to use this non-relativistic expansion. The idea here is that NRQCD tells us that parametrically, the heavy quark velocity is of the same order as the coupling constant or slightly larger. And this allows us to write an expansion in terms of V and alpha S. And we can do this systematically using this non-relativistic expansion by Miguel and Thomas. So here, if you want the total wave function for Fock state n, you can write it in terms of this leading order wave function for Fock state n. So in terms of Feynman diagrams, this blue blob here is the leading order wave function. And when we add these Feynman diagram corrections to it, we get the total wave function. And here in this expansion, the alpha S corrections are included in this function C. And then these derivatives tell us about the velocity suppression. So this index K is basically the power of the velocity in this expansion. And in this talk, we consider the next to leading order corrections in alpha S in the non-relativistic limit to Chase-I production. And the relativistic corrections at V squared in the leading order were calculated in our previous paper with Thomas and Heikki. So now the next to leading order corrections that we need are these. So we need this wave function for the Fock state QQ par and QQ par G at next to leading order. And in the non-relativistic limit, we only need this integral over the leading order wave function of the Fock state QQ par. So basically there's only one non-perturbative constant here in our equations. And then these C functions have to be calculated at the next to leading order, as was done by Miguel and Thomas. And there you need to take Feynman diagrams like these into account. So for the QQ par state, you get virtual gluon loops. And for this QQ par G, you get an emission of a real gluon. And these same Feynman diagrams are also present in the calculation for the virtual photon wave function at next to leading order. So after we have all this, we can actually calculate the production amplitude at next to leading order. And so far we have done this for the longitudinal case. and we are still calculating the transverse case, but the transverse case is really similar to the longitudinal one. And in this calculation, we get some ultraviolet and infrared divergences. So separately, these QQ and QQ parts of the calculation are UV divergent, but it turns out that their sum is UV finite. And then our final result should also be infrared finite. But to have that, we need to take into account several more things. So first of all, we need to renormalize this leading order wave function. And this can be done using this leptonic decay width of the JSI. So if you write the leptonic width at NLO, you can then see that there's this divergence. And you can actually solve this leading order wave function in terms of the decay width. And then we also get rid of this non-perturbative constant in our equations. And another thing that one needs to take into account is this energy dependence of the dipole amplitude, so the Balch-Goldskov equation. And after all this, we get something that is finite and can be used for numerical evaluations. So let me briefly show you the final result that we get. So here's the leading order part, and then this next to leading order corrections, which are rather complicated. So we have to evaluate this numerically. And here I have plotted the production amplitude in terms of the center of mass energy, W. So here are the leading order and next to leading order results. And we find that the NLO corrections are large, about 75% of this leading order result. Therefore, there's a significant increase of the amplitude. However, I should mention that in this calculation, we use the same dipole amplitude for both the leading order and next to leading order case. And this is not actually consistent, as I will demonstrate next. So remember that in this dipole amplitudes, you need an initial condition that has to be taken from a fit. So here we use a fit to Hera structure function data. And when you do the fit, you can use the leading order or next to leading order equations for the structure functions. So here this LOPK uses the leading order equations for the structure functions, whereas these other ones use the next to leading order equations for the structure functions when doing the fit for the initial condition. And then you should use, when calculating the production amplitude at leading order, you should use this leading order fit. And when you calculate the next to leading order, you should use this next to leading order fit. So what we have done, what we have plotted here is that we plot the differential cross-section as a function of W. And here we show the leading order result with the leading order fit and the next to leading order results with the next to leading order fits. And in the lower plot, we have divided the results by the leading order result. And in this case, you can see that there's only about 20% difference between the NLO and leading order. So this is a lot less than what would be judged by the production amplitude plot. So this tells us that the leading order dipole amplitude fit can compensate for this NLO effects. And it also tells us that it's important to use the fit with the correct order. But another thing that we see here is that there's some deviation between these NLO results. So remember that they were fitted to the structure function data, so they should agree well there. But this tells us that this vector meson production gives us some additional information to this structure function analysis. And this is because in this process, we probe the nuclear structure at different length scales than what is done in the structure function analysis. And then we also wanted to compare these next to leading order corrections to the relativistic corrections. So as I mentioned earlier, the relativistic corrections of order v squared were calculated in our previous paper. And now here in this plot, we have the differential cross-section as a function of the photon virtuality. And in black, we have the leading order results, and in red, the next to leading order ones. And solid lines are the fully non-relativistic cases, whereas the dashed lines have the relativistic corrections of order v squared. And these error bands also come from the uncertainties of these relativistic corrections. And in the lower plot, we have divided this by the leading order result in the non-relativistic case. So first of all, what we see here is that at next to leading order, these relativistic corrections are less important than at leading order. And this is because at next to leading order, we of course have these large NLO corrections. So the relativistic corrections are smaller in comparison. And at small values of the photon virtuality, the relativistic corrections are actually larger than the NLO corrections. And this was because the dipole amplitude fit compensated for this next to leading order effects. But when we look at large Q squared, first of all, these relativistic corrections become insignificant. And then these next to leading order corrections actually grow larger. And this is because there's actually a different rapidity evolution in the dipole amplitude between the leading order and next to leading order results. So in summary, we calculate the next to leading order corrections to longitudinal heavy vector meson production. And we found that the NLO corrections are significant, but the leading order dipole amplitude fit can capture most of these next to leading order effects. And there were also some deviations between the different NLO fits. And this tells us about the complementarity to structure functions, structure function analysis. So this vector meson production gives us some new information. And in the future, we also want to calculate the transverse production, as this will then allow us to compare these next to leading order results to the data. And finally, I would like to mention that these are important developments as we expect to get precise measurements from both the LHC and the future electron-ion collider. Thank you.
Thank you very much for this very nice talk and this also very nice result you present here. There's really one question here by Farid. So please, Farid, go ahead.
Hi, Gianni. Yes, very nice talk. I have a question about, I think it's a slide 9.
This one?
Yes, this one. So in the bottom plot, you show that there are significant deviations between these 4 implementations, 3 implementations of NLO BK and the LO BK. And you mentioned that this is probably due to the fact that you are measuring different sizes, right?
Yeah.
So my question is the following. These fits that you use are for the F2 for light quarks, right?
Yeah.
So if you guys were to do the fit to F2 charm, how would you expect these results to change? Because if you do F2 charm, then you also have the mass of the charm quarks, and that probably you won't see much difference. Is that your expectation?
Yeah, I don't really have any clue how it might change things, but it is true that in the future we should do also fits including the charm quark mass, because the fits are done using the photon wave function that hasn't the quark masses implemented yet.
Right. So yeah, I was just expecting that if you were to do F2 charm, then the scales probed would be perhaps closer to the scales that are probed here in the JSI production?
Perhaps, but there's also the difference that in the structure functions you only have the photon wave function, but here you also have the meson wave function, which changes the scales that you probe. But it's true that they might be closer to each other then.
I see. Thanks.
Okay, so again, thanks a lot for this nice talk. I think there's no more further questions, and I think we should go on in the schedule. But again, thank you very much. The next talk is by Jair Mulyan on forward digits in proton nucleus collisions at the next leading order. And if you're ready, please share the slides.
Okay. Now you see the slides, right?
Yeah, great. Now it's all perfect.
Okay, so my talk will be based on two papers that I published together with Edmond Yanku, in which we have calculated the NLO digit production in proton nucleus collisions. So the basic setup that we are trying to explore is shown at the bottom of the slide. We have a proton colliding with a nucleus, and two jets are generated in this process. Kinematically speaking, we are looking for the case that low X gluon is emitted from a large X constituent quark, and that will allow us to use the shockwave method in order to describe the interaction with the target nucleus, which means that basically the interaction with the target will be by color rotation of the parton that is interacting with the target, or basically just having a Wilson lines that will affect the change of it. So the first one who dealt with this case is Cyril Marquette. He did this already 15 years ago, and he obtained the result for the leading order cross section. The paper in which he did this is shown here. And we were interested to find the NLO correction of his result. In order to do that, we adopted a slightly different approach known as the light cone outgoing state. And we also used the CGC effective theory together with hybrid factorization. Now, what is this light cone outgoing state approach? We can discuss now in this slide. So we all know that if we have an incoming state, we can find its time evolution by acting with a unitary time operator shown here, which is dictated by a Schrödinger equation. And the essence of this method that we are using is to realize that the state which encodes both the time evolution as well as the interaction with the target nucleus is given by a triple product. So this triple product is defined here. So we act on this incoming state with the unitary time evolution, which allow us to transit from -infinite to the time of the scattering, which we denote by 0. Then we act with this S, which is the scattering operator. This will dress the partons with the Wilson lines. And then we allow the state to evolve from the time of the scattering to the final state, which is at infinite. Once we have this outgoing state, we can basically find any expectation values by plugging it in the definition at the bottom of the slide. Now let us see in more details the case of leading order. So in order to see what is going on there, we have to expand this unitary time evolution operator up to order G. And this will give us two new terms. We collectively write them together in this psi. And I'm not going to give the details, but once we fully compute this state, this contribution, the result will end up here. Now, this might look a little bit complicated at first sight, but it can be almost fully justified based on physics behind this state. So, for example, we can see that in the yellow box, we have this, call it root square of this D-glop splitting function. In green, we have the Weizsäcker-Williams field. And in brown, this is the condition that the center of the mass of the incoming parton state will remain the same as the center of the mass of the outgoing quark state and the gluon. And in this red box, we have combinations of Wilson lines. Now, the Wilson line in the fundamental representation, we write it as V, and the Wilson line in the adjoint representation is denoted by U, and this will take care of the color rotation of the gluon. Now, once we have this leading order outgoing state, we can look what is the respective cross-section. So at leading order, the only cross-section that we can have is initiated by a quark parton and a gluon parton, which means that it is defined by the following relation shown here. We can now plug inside this definition the result for the leading order outgoing state, and what we find is exactly the same result that Cyril found, which is shown here. Again, this result might seem a little complicated, but can be mostly justified. We can see here this alpha S, which is obviously what we expected. This CF is what we can expect based on the large NC counting. In yellow, this is the D-glop splitting function for a quark emitting a gluon. And here is the criteria for energy conservation. And then in this green, we find the Weizsäcker-Williams field in the amplitude as well as the conjugate amplitude. In blue, this is the Fourier transform, which we find since we want to write the result in the coordinate space. And in red, we find some bunch of contractions of Wilson lines. And basically what we note is that we have interaction between dipole and quadrupole and dipole-dipole. Now, each of these 4 contributions will correspond to a different contribution. For example, we note this contribution here, this dipole-dipole, corresponding to the following insertion. But of course, other cases, for example, correspond. For example, the case that the quadrupole dipole corresponding to case of shockwave acting on the quark gluon on amplitude as well as the conjugate amplitude. And these contractions, the dipole and the quadrupole, are defined by the following definition here and here. And we can easily find the jet cross-section, that dijet cross-section, by convoluting the partonic cross-section with PDF as shown in this relation. And we can even take it one step further and find the hadronic cross-section by convoluting this result with the fragmentation functions. Now, as I mentioned, our interest was to find the NLO dijet production. And in order to find it, we had to first analyze the case of trijet. In order to realize what is going on there, we first have to look what will happen when we allow one more step in the time evolution. That means that now we are going to deal with cases that is shown at the bottom of the slide, one typical example. So the gluon can emit, so can split into two other gluons via this triple gluon vertex. But of course, this is not the only case. We can definitely generate one more gluon from the same quark, or instead of generating two gluons, we can also generate a quark and anti-quark. So we have to take care of all the possible scenarios, and we have to sum them together. One more thing to note is that since we are using the light cone gauge, we can also generate two gluons instantaneously without passing through an intermediate gluon. This is one of the peculiarities that we are using, that we find since we are using this specific gauge, and we have to take care of this as well. So diagrammatically, we are talking about the following diagrams, which you can see here. And once we have them, and once we compute them, we can find the partial contributions to the trijet cross-section by plugging them inside the following two relations. So this is the relation for having a quark, quark, anti-quark, or a quark plus two gluons. And of course, we can pass from this partonic cross-section to the jet cross-section by convoluting these partial contributions with the PDF. Now we can see why it was interesting for us to find the trijet cross-section. Basically, there is a very interesting relation that if we integrate out one of these unmeasured partons, we can directly find the real contributions for the dijet production. And this is exactly what we did in our paper. I'm going to show you some partial result for the case of quark, quark plus anti-quark. So you will realize the structure that we find. The other case having some similar properties. So it makes sense to explain a little bit what we found. So now what we see is that we not having only this Weizsäcker-Wilhelms field. In addition, now we find here this piece, which is this tensorial kernel. It will be defined in the next slide. And in addition, we find a color structure, which now involving 6 coordinates. So 3 coordinates in the amplitude plus 3 in the conjugate. This is somewhat similar to the case of leading order, but plus 2 coordinates. So again, the color structure here can still be fully written by using only the dipole and the quadrupole. In addition, we find some subtraction terms. These terms will correspond to different insertions of shock waves. So, for example, this case that Z and Z prime going to coordinate Y, which is their center of the mass, is corresponding to the case that this quark anti-quark shrinks. And effectively, this is so this is identical to the case that the shock wave is affecting the gluon rather than this quark anti-quark. So we had to take care of course, of the case of the conjugate subtraction, as well as the case that we have this contraction on both the amplitude and the conjugate. In addition to that, since we deal with case of 2 quarks, we had to take care of this purple term, which is their symmetric change. Now here some definitions. So the tensorial kernel is defined by a product of 2 effective vertices, which we denote here by some capital phi, defined by this definition. And basically this phi takes care of both the regular as well as the instantaneous emission. The color structure, as I mentioned, is given by some interactions between quadrupole and dipole. And we have to define 2 kinematical variables, which is var theta and psi, which take care of the fraction of the parton plus momentum to the plus momentum of the incoming quark. Now we can see in more details what this z prime goes to their center of the mass, how it affects the result. So basically it affects two pieces. So the first thing to note is the energy denominator. Once we make this replacement, this term, this capital Z, which is defined by Z minus Z prime, so this quantity will vanish and we will left with a simplified energy denominator. And the Wilson lines will also be replaced by, so instead of two Wilson lines in the fundamental representation, we will have Wilson line in the adjoint representation. Basically, we shifted the shock wave to the position of the gluon. Of course, if we want to find the full result, we have to take care of many more cases, many more contributions, and some of them are shown in this slide here. I will quickly mention what are the divergences that one meets when is dealing with such calculation. So we have some short distance poles. These are generated when two partons are approaching each other, and these will be cancelled generally by pairing diagrams. We have this collinear divergence, and this is the case when partons are emitted far away from each other. I'm going to discuss this a little bit later. And these contributions will be reabsorbed in the DGLAP of the incoming PDF or the outgoing fragmentation functions. And in addition, there are two other divergences, the UV divergences and the soft divergences. These will not be relevant for the current real contributions, but they are a very important part of the virtual contributions. Now, once we have this result, the result for the either trijet or the real dijet, analog dijet, since the result is quite complicated, it makes sense to make some checks. And a very natural check to do is to try to recover gym walk evolution. In order to see that we, in fact, managed to do it correctly, we took our result and we assumed, and we checked the limit that a gluon is becoming soft. I mean, any possible gluon. So we checked all the possible cases, and we managed to show that indeed, when we are taking such limit, it is possible to write the result as G-walk evolution of the result that Cyril found. Let me be a bit more precise. So, for example, at the top of the slide, you can see some 4 diagrams. And once you take the limit that psi is a small parameter, basically you assume that psi is much smaller than 1, it is possible to rewrite the result in our paper by the following structure, which you can see here. And basically, this is something that you can immediately recognize. So here in this red box, you can see piece of the leading order result. And in addition to that, you can see in the red box, the BK evolution of the dipole. So you remember dipole was the last term in the color structure of the leading order result. So this was one piece. For example, another case that also appear in the paper is the case that we take the limit of a soft gluon for this bunch of diagrams. And again, even in this case, we managed to show that the result is still factorizable to a leading order contribution and a BK evolution of quadrupole dipole, which is, you can see here. Now another check, or something that one wants to see is what is happening in the collinear limit. So in this limit, the separation between partons become arbitrarily large. And of course, we expected to recover a D-glap evolution of the incoming or final quark state distribution. And what I can show you, what I'm going to show you in the next slide is the case of the diagrams that are appearing in the bottom of the slide together with the diagram here. So we took this collinear limit and we managed to show that the result is becoming a little bit more simplified to the following version. And this is exactly the result which one obtains by one real step in the D-glap evolution of the quark distribution inside the proton. So up to here was the matter of the recent paper I published with Edmond. And from now on is another paper that is currently still, we are working on it and we hope to publish it soon. In this paper, we are dealing with the virtual contributions. Now, these contributions are a little bit more complicated. This is due to the fact that we can really have here a full loop. And that means that we have to take care, we see both UV and infrared divergences. So the first one who dealt with this case, Thomas Lappi and Risto, and they published a paper on it. Unfortunately, we are using different ways and different way of a momentum assignment, and we had to recalculate things. And I'm going to show you one typical example of the contributions that we find for these virtual contributions. For this case, let us look more closely on the case of gluon loop. And what we see is now we have some logs, so these infrared logs, and this parameter here, lambda, is a parameter which is we are taking to 0. So there are two kinds of logs. So this log times this transverse log and this log squared that appear here. But what we managed to show is that if we combine together all the different contributions that are relevant for this case, so all these virtual contributions, the coefficient of these infrared logs is vanishing. So that means that they will give us finite contribution to the cross-section. This is what we originally expected. And we managed to use this finite piece in order to compute the relevant contribution to the cross-section. And the result that we find is interesting. It shares a quite similar structure as the leading order, but in the additional part is encoded in this K. So this kernel. So this kernel encodes information both on the beta function as well as the cusp anomalous dimension, which is encoded here. But this is not the ordinary cusp anomalous dimension, because this cusp anomalous dimension have additional terms due to the fact that we did not use equal assumption on the kinematics of the process. So that's about the virtual contributions to the NLO dijet. And we recently start to think what's next. So what might be interesting to explore after this project will be done. And it turns out that might be very interesting to check what will happen when we are replacing this incoming quark by an incoming gluon. So some of the diagrams which are relevant for this channel are shown here. We are considering to compute them and to see their result for the cross section. So this is one option, and other option which is very interesting for the EIC is to use the result that we found for this outgoing state. And so we basically computed the part which is in here in the red box, but this can be dressed by using some result that Guillaume found. So Guillaume computed the leading order virtual photon state, and we can basically use it to promote his result for the level of NNLO. That is something very interesting because we can find many interesting observables for EIC. So that is another option that we consider, to do the transition from PA to EA, basically. So here's a quick summary of my talk. I will leave it here, and I will be happy to hear any question, basically. So.
Yeah, thank you very much for this nice talk. Again, we already got a first question by Farid, so please, Farid.
Hi, Jair. Yeah,
Hi, hello.
I enjoy your talk.
Thank you.
As you know, we are also interested in these NLO computations for digits, but in DIS. And my question is, in the implementation of the real contributions for the computation that you're doing, why didn't you implement JET algorithm? Why did you guys choose to go through the route of DGLAB?
I mean, it's still necessary to do that. It's just that we left it at this step. But of course, if one wants to really compare and to do phenomenology, he has to use some JET algorithm. We were mostly interested to compute and to check the mathematical structure as well as the physics behind it. But of course, this is a necessary step that it's not avoidable. We consider to do it as well. It's not something.
Yes, right. So I mean, my question is because as you said, there is going to be a collinear divergence, right? Which in your case will be absorbed in the fragmentation functions of the final state.
Yes.
An alternative, I mean, this is great, but an alternative would be to absorb this collinear divergence by imposing some JET algorithm, for example. The simplest case, which is what we are trying to follow, is like a small cone approximation.
I mean, there are many ways to regularize things. It's not something that is, it's not, there is not only one option, there is more than one. Even for example, for the virtual case, we are using a sharp cutoff and dim-reg, but of course you can use, there are various techniques to regularize what is going on there. But, and of course, the same thing is here. You can use other ways to deal with the collinear divergence.
Right, I see. So in this case, you wanted to see the mathematical structure for the DGLAB evolution, which, okay, that's very, very interesting. Okay. And
anyway, we should talk, Farid. I mean, maybe we can collaborate on something I think is interesting for us.
I have one more question, and perhaps it's a bit beyond the scope. But you mentioned this gluon initiated channel.
Right.
Right. So in this case, would you have to consider the fact that the gluon the incoming gluon may carry non-zero transverse momentum? So just to be sure, right, in the quark-initiated channel, you are assuming the quark is collinear, right? It doesn't carry transverse momentum. Is that correct?
So originally, the result is computed by. We do not assume that. We assume that we impose it. We impose it, but the result it's not a big deal. I mean, to make a transition and to write the result in the case of non-zero incoming transverse momentum. This is just something we impose at some point.
Okay, so it's a choice of a frame, I guess, in which you choose.
Exactly. So it's a frame that you are preferring to work with, but in general, it does not make your life. I mean, it's not a big deal to find a result for non-vanishing.
Right. I'm wondering, in the case in which it carries some non-zero transverse momentum, what will have to integrate, right? So it's not like DIS where the photon is fixed. The virtual photon kinematics are fixed by the electron, right? If you know the incoming electron kinematics and the outgoing, you can fix.
Right.
But here, you really have to integrate.
Yeah, it's a PDF basically of the income.
Yes. Or like, I don't know, maybe some TMD or whatever that carries the information about the transverse momentum of the gluons.
Right.
Yeah, I think it's a little bit tricky. It's not just a matter of, maybe, I haven't thought it too deeply, but maybe it's not just a matter of choosing a frame.
Could be true. I mean, I agree with you that this is not something that you want to impose trivially without checking that this is a valid assumption. But anyway, this is not something that we are starting to work with. I mean, we do not impose this at the beginning, but rather at the very end. So yes. I think I am more afraid of the virtual case of these gluon contributions. I mean, they are quite challenging loops that looks formidable to me. But so the case of real contributions for the gluon channel can be done quite easily. It's not a big deal, but there are some challenging virtual loops that.
Yeah, this is extremely courageous work like this. Yeah.
Yes, I think it might be interesting, but it definitely not something that you find it trivially.
Yes, thanks, Eric.
Yeah, thank you very much for this. Yeah, for this nice discussion here. I think we came now to the end of our program. I mean, in case of no more questions, of course, when somebody wants to ask a question still, your chance.
Yes. So yeah. So I think it's starting to be.